Wondering if you have your memorabilia yet for the upcoming championship award. Oh, it's gonna happen soon. Hey folks, welcome back to part 2 of lesson 96. We're gonna do a little bit of stuff with the graphing calculators today. Just quickly in review, we were graphing them by hand by using the information embedded in our function ax squared plus bx plus c. We take the letters a, b, and c, or really the coefficients a, b, and c, the constant c, and define the axis of symmetry because all parabolas are symmetrical. We take b, negative b over 2a, and there's our dotted line of symmetry. It'll look the same on the left as it does on the right to that line. We use that value there in the axis of symmetry. That is our x point for our vertex, the highest or lowest point on the parabola. And evaluate the function. We plug in that number, whatever it was, into the function, and whatever comes out, that's the y value for the vertex. We had a third value that we looked for, and that would be the y-intercept, where it crosses the y-axis. And that will be at the point x is 0, y is c, and I mean like this c right here. We are going to talk about a fourth one here after we do this stuff on the camera, and then I'll be talking about zeros. Also, we were looking at variety of forms of quadratic equations. We could take our easiest one where a equals 1, and that means we could just write it as x squared plus bx plus c. Example that we worked with was x squared plus 4x plus 5. Also, we looked at if a is not just 1, like it's some other value that sits out in front of our equation. An example of that I'll use later on is 3x squared plus 2x plus 6. And then we're also going to get to this, and this will be a little bit easier to show on the calculators. But what if the b portion of it is 0? It means there's no plus bx in there. It's just ax squared plus a constant. To give you an example of that, would be 5x squared plus 4. So I'm going to go ahead and show you what those will look like on the graphing calculator, and what each value of a, b, or c, if we move it, change it individually, what does that do to the picture of the graph? I want to show you that. And then we'll come back onto the board and talk about zeros. So that's what we got to look forward to. Let me switch over to the other camera so we can look down on the calculator and in the cell phone. Welcome back. You got my TI-84 out here, and Strong Guy's going to help. I'm happy to help you. Okay, folks, so here we go. We're going to go over to our y equals editor, and I've already got my function in here for the first form of x squared plus bx plus c. We see that we're using a b is 4 and our c is 5. I'm going to make sure that I zoom 6 this sucker. Zoom 6 is zoom standard. And we got our grid, and here comes the graph. Okay, just our normal parabola. What I want to know, oh golly, its axis is off. Format, let's get that axis on. Yeah, how about that? Sure. Okay, there we go. So I was doing some coding. All right, there we go. A few things that we want to note about that would be axis of symmetry, vertex, and maybe a y-intercept. Those three things we were looking at before. The first thing I probably have to do on this one is actually find the vertex, and that's pretty easy. We go second and trace, so we're getting to the calculate button there. And on this one, since it opens up, it does have a minimum value. That minimum value will be the vertex. I just have to give it where to go to check for it. So I'm going to move my cursor a little bit to the left and hit enter. Use my arrows, go a little bit around the corner to the right, and then I'm going to guess that the vertex is right about there. And it tells me that the minimum is actually, looks like it's negative 2 and 1. Negative 2, 1. This tells me two things. Vertex has an address, negative 2, 1, and it tells me that the axis of symmetry is when x equals negative 2. So there's two things out of the way by using second calculate, finding the minimum here. The minimum is the vertex, and the x part of the address for the vertex is our axis of symmetry. And the only other thing we had to do after that was figure out what that y-intercept value is. And you can find that by hitting the trace button and then asking it for when x equals 0. You just type in the number 0. Okay, so x equals 0. That is the y-axis. Hit enter. It looks like it's at 0, 5. Gives you enough information there that you could sketch that picture pretty quickly. All right, I'm going to go in here. I'm going to change that one to a different formula. I'll use the second one I had, 3x squared plus 2x plus 6. And maybe we want to predict a little bit of what this is going to look like, or maybe not. Maybe we're just going to hit graph because we want this to do the graphing for us. And there it is, way up there. Okay, so we're going to do the same thing. We're going to go second calculate. This also opens up so it has a minimum. And I'm going to give it a left bound and a right bound. Those little arrows then say it's looking for a lowest point between those 2 points. And it says that the minimum is a negative 1/3. And it looks like 5 2/3. Okay? The x address there is my axis of symmetry at negative 1/3. And lastly, we would like to find out where that crosses the y-axis. It looks like it's oh, there it is. It gives it right to me. Remove my arrows and it right away tells me that's at 0, 6. Or I could say trace. I can type in, tell me when x is 0, and it puts the cursor right there, and the address is right down here at the bottom at 0, 6. Go to the last type. I'll go back in here and change it. And I'll have 5x squared, clear all this stuff, 5x squared plus 4. Want to graph that? It's right down the middle and symmetrical to the y-axis. There's a couple things I ought to know about that then. My minimum, or vertex, is going to be on the y-axis. That means that its x address is x equals 0. And also, it crosses at 4. I can tell some things about it already. Now, if I want to double check, I can say, let's look at that minimum. Give it a left bound and a right bound, but it's right there. That's basically 0, and that's 4. I can double check on that by tracing it, and it gives me 0, 4 as the low point there. Axis of symmetry, then, x equals 0, or the y-axis. Now, where does it cross the axis? Well, right there, I already have 0, 4. And the reason for that is because this part right here is basically our friends, the basic kind of like parent function that's been dilated. And then we take that function and we move it up 4. Or, if we like to, we can move it down 2. So I want to graph it. It'll be the same thing, except it's going to be down there. Now, if I want to like maybe graph one on top of the other one, let's do 5x squared, and this time let's go up 3. So the first one here comes in and it is the same exact thing, just shifted up 3. Maybe I want to shift it down even some more. I'll just increase this to like negative 4. And there's the first one, and there's the second one, and it crosses now down at negative 4. So that last part, that C part, just shifts your picture up or down. It'll be a little bit easier for me to demonstrate that on the cell phone. So let me switch that out here, and we'll check it out. So hang on. Okay, here's Desmos, and I've got it set for a standard ax squared plus bx plus c type of equation. And I have these things here called sliders. I can change the values of a, b, and c as I'm watching. So if I want to do that very last one, I'll set a to be equal to 5, and I'll set c equal to 4. And we see that up it creeps, 4.2, whatever. Nice thing about Desmos is once you get it, you can kind of like tap on the picture or move the picture, and it'll automatically give you that point and make it stay right there. Now what I'm going to do first is I'm going to just let C change. Okay, I'm going to let C change, and so I'm going to press the play button, and C is going up, and then C is going down. You can see exactly what it makes that picture do. Okay, it's going way down, and here it comes back up. The parabola is not changing shape, it's just rising and it's falling. I'm going to get it stopped somewhere around 4 again. Trying. Okay, that's what C does. When C changes, it makes your whole picture go up or down. Now what happens when B changes? Well, I start with B equals 0, but look what happens to this if I make B bigger. It kind of slides around here, but that one point stays the same. And it kind of like traces around that point. So if I make the play thing go, this is what B does. If B gets bigger, it slides over this way. If B gets smaller, it slides over this way around that one point, that intersect point at 4. Well, I can change that intersect point by lowering it down, maybe to 1. Maybe. There we go. And now it just rotates around that point 1 as I change B. Okay, there we go. It's stop. And let's see. Let's make B equals 0 again, so it's right in the middle. Oh, it's close to there. Last thing I'm going to do is going to manipulate A. And as A changes it, A gets bigger, it makes it skinnier. And as A gets smaller, it makes it wider. Oh, now it's negative and it flips it upside down. So there's kind of like a picture version of what happens as you change A, or as you change B's value, or if you were to change C's value. Or what about if you're changing them all at the same time? Wouldn't that be fun? There you go, at different rates. And it's getting skinnier, it's getting wider, it's rotating around a point that's moving. Oh, now it's upside down. It's like a roller coaster. My goodness, look at that thing change. Whoa, where did it go? Oh, my word. All right. It's kind of the shorthand version of what goes on. We need to talk about one more thing, and that's zeros. Right, you still there? All right, I am too. Okay, let's talk about those zeros. Here's our definition. You want to pause? Okay, an x value for a function where when you plug in that number into the function, the answer comes out being 0. That means when y equals 0. And where does y equal 0? It does right here. So another way of talking about a 0 is an x-intercept. An x-intercept. Give you a quick example of one way you can find one of those. Let's take the equation x squared minus 6x plus 9. A quick way to do it, besides graphing, that's easy, you can do zeros on your graphing calculator, is to factor this. And this is of the particular form x minus 3 times x minus 3. Now you tell me, what's going to make this equation equal 0? Well, if I put in a 3 right there, or I guess right there, so really this one only has 1, 0. If I plug in the number 3 into x squared minus 6 times 3 plus 9, I get 0. Then the graph of that looks like this. And it only touches right there at x equals 3. Now that's an example of a type of graph that only has 1, 0, which is like our parent function. It only has 1, 0 because it comes down and it only touches the x-axis at one place. But just imagine if I drop that down 4 places and do something like this, now it would cross at 2 places. That would be like that. Or if I raise it up, way up here, it doesn't cross at all. So we have 3 different possibilities for zeros. We can have 0, 1, or 2. There you are.